Okay, let's look now at chapter 18. Why does it do this? All right. So chapter 18, page 653, where we're going to start. Let's look at number 11. Okay. We got a ray of light impinges on a mirror as shown in figure 18.11. Okay, so here's what our figure looks like. So we got a ray of light coming in here like this. Whoops. And this angle right here is 35 degrees. Okay. All right. A second mirror is fastened at 90 degrees. So here's your second mirror. So here's a mirror, and here's a mirror. Okay, right there. Now, y'all, the mirrors are flat. Okay, I know I didn't draw it perfectly flat, but it's flat. Okay, it's straight up and down. And it says 90 degrees. After striking both mirrors, at what angle relative to the incoming ray does the outgoing ray emerge? Okay. All right, so remember now, we always measure relative to the normal, and the normal is perpendicular to the surface, right? There's your normal. All right, so if this angle is 35, then this angle right here has to be what? That has to be 55 degrees. This is actually just some geometry here, okay? All right, because what do you get? You get 90 degrees, don't you? All right, so then we come back off and come over here and hits this mirror, and y'all, I'm sorry, but that aggravates a fire out of me. Let me see if I can draw this a little bit better. All right, so the ray comes in, hits the mirror, and comes over here. I'm trying to draw it as straight as I can. So this angle, now look, these are congruent, even though it don't look like it. Try it one more time. I give up. Okay, so this angle is what? Well, according to geometry, that angle's 35, and then this angle is what? 55 degrees, isn't it? Okay. All right, well, all right, now, let's remember our geometry. We're hitting this side over here. So if this angle right here is 35, by the way, we need to draw a normal, don't we? Yep, sure do. There's your normal right there. Okay, so if this angle right here is 35, what is that angle right there? Well, that's got to be 35, right? Remember your geometry now, opposite. All right, opposite adjacent angles, opposite or congruent. I can't remember the exact postulate, but you know what I'm talking about. These are congruent angles, okay? I remember the geometry. I just don't remember exactly what the theorem says, the postulate or theorem says, okay? So then that means this angle right here has to be 55 degrees, okay? And if you remember, however an angle hits, when you have specular reflection, okay, when you have perfect reflection, this angle and this angle has to be equal, doesn't it? So that angle's 35, and this one is what? 55. Okay, so that's a good little practice in geometry, isn't it? All right, all right. I like those kind of problems. Okay, they're not hard. Okay, let's look at number 12. Okay, number 12, still on the same page, 653. All right, it says we've got an underwater diver sees the sun 50 degrees above the horizontal. How high is the sun above the horizon to a fisherman in a boat above the diver? Okay, well, let's just draw this here now. So we got the surface of the water there, and we got our boat right here and our fisherman right there, okay? And we got the diver right here. Goodness gracious, what's wrong with him? I think I might have to recalibrate my pen. Okay, so we got the diver right here. Whatever. All right, he's directly beneath the fisherman, okay? So, all right, we're going to go from his eyes now. So, let's draw a plane here. All right, we've already got the vertical. That's vertical, just imagine, okay? So he sees it what? Well, he sees the sun 50 degrees above the horizontal. Well, where's the horizontal? This is the horizontal right here, horizontal. So that means he sees it right here. This is 50 degrees, okay, above the horizontal. That means this angle right here is what? That angle right there is 40 degrees, isn't it? Okay. All right. And so then you have the guy on the surface. Now, what is the light going to do? Let's draw another. Man, it's getting aggravating now. I'm going to have to recalibrate. I'll do that after this video. I'll try. Okay, got to draw another normal. And so what is that light ray going to do when it, now notice that the end of the water is higher than the end of the air. The end of the water is probably like 1.33. The end of the air, we know the end of air is what? We're just going to say it's 1. The end of water is probably going to be 1.33. Matter of fact, I know it is. The end of water is 1.33. We looked that up in our table in our book, okay? So what's it going to do? When it's going from a index of refraction of higher to lower, it bends what way? It bends away from the normal, doesn't it? So when you go from an index of refraction that's high to an index of refraction that's low, you go from a high medium index refraction to a low medium index refraction, then it bends away from the normal. If it's the other way around, if you're going from a low medium index of refraction to a high medium of index refraction, it does what? The light ray bends towards. It's refracted towards the normal, okay? Okay. All right, so we got an angle here, and we got an angle here, and we got an angle there, don't we? Okay, so how on God's earth are we going to find this angle? All right, let's read it again. It says, how high is the sun above the horizon to a fisherman in a boat above the water? Notice he wants to know how high above the horizon, okay? So he really wants to know this angle right here, doesn't he? Okay, because see, he's on there, he's on the horizon. So how, and this is the horizon, by the way. This is the horizon to the fisherman. This is the horizon to the diver, all right? So basically, what are we going to do? We're going to use Snell's law, and we know that Snell's law is what? The n of air times the sine of the angle in air, okay, is equal to the n of the medium, in this case water, times the sine of the angle in water, okay? And so what are we looking at now? So we're wanting to know what the angle is in the air, aren't we? Okay? We are wanting to know what the angle is in the air. Well, hang on. We've got to find these other angles, don't we? Well, we know this angle right here is 40 degrees, don't we? We know this angle, but we don't know what this angle is, do we? No, we don't. And if we don't know this angle, we don't know this angle. Once we find this angle, we can find that angle. Now remember, Snell's law deals with angles with respect to the normal. Please remember that. It's the angles with respect to the normal. Okay? Okay, please remember that. So we are looking for what? We're looking for the one in air, correct? Yes, we are looking for this right here. That's what we're looking for. So we are looking for theta air, right? Question mark. All right, well, let's just solve it for that. Okay, so we take then the theta. Let's do it this way first. Sine theta of air is equal to what? All right, well, that's the normal of the water times the sine of the angle in the water divided by what? The n of the air, the index refraction of the air, and then to finish working it out, we take theta, and we're going to do what? Arc sine, aren't we? So it's sine -1 of n of the water times the sine of the angle of the water divided by the n of air, right? So let's come over here and plug it in. All right, so we get now, we've got arc sine or inverse sine of what? Well, the n of the water was 1.33, so we got 1.33 times what? The sine of 40 degrees. You said, where'd you get that? Look right here, y'all. If the angle with the horizontal of the diver that he's seeing from the horizontal is 50, then the angle from the normal has to be 40, because you got to get 90 degrees when you add them together. Okay, and then of course the next part's easy because it's 1, because the index fraction of air is 1. And so when we do all that crazy, wonderful arithmetic, what do we get? Okay, all right, well, we get 1.33 times sine of 40, okay? And then divide that by 1, and that's going to be whatever the answer is, which is 0.85, and then we take the arc sine of that, and we get 58.7 degrees, okay? So we get 58.7 degrees. Okay, now hang on a minute. That is what? All right? Now you say, well, that's the final answer. No, it is not. That is this angle right here, 58.7 degrees. Okay, because remember, y'all, Snell's law, you've got to remember that it was derived by taking the angle with respect to the normal. Okay, well, we want to know what the angle is with the horizon. Well, that's easy. All we got to do is do what? To find the angle of the horizon, okay, we take the angle with the horizon, and that's going to be what? 90 minus 58.7, and what do we get? We get 31.3, okay? So it's 31.3 degrees above the horizon, okay? All right, and there you go. So you got to pay attention now to what the question's asking for. Notice it said, what is the angle above the horizon? It didn't just say, what is the angle? Okay, remember, Snell's law deals with angles that are with respect to the normal. Okay, all right, so don't forget that. That's not a trick question, okay? If you understand the concept of Snell's law, you should know that. Okay. All right, that's why I said it like 12 times. All right, so now let's look at number 25. Where are we at? Yeah, number 25. Okay, so we got 25, and that is on page 653. All right, same page. It says a biologist keeps a specimen of his favorite beetle embedded in a cube of polystyrene plastic. Okay, the hapless bug appears to be 2 centimeters within the plastic. So we got a bug here, and we got a little bug here. Okay, there he is, and a leg and whatever. Okay, there he is in the plastic. And the hapless bug appears to be 2 centimeters within the plastic. Okay, so in other words, S prime is what? What did I say? 2 centimeters? Yeah, 2 centimeters within the plastic. Boy, that just doesn't look too great. Oh, shoot. Let's start over. All right, so we got, dang it, we got number 25. I'm sorry, y'all. So you got your bug. Okay, there he is. All right. And the S prime is 2 centimeters. All right. Okay. And we want to know what S is. We want to know what the actual distance is. S is the actual distance. All right. Well, we are using equation 18.7. And so then what? The S prime of an object, in other words, the image distance, S prime is image, this is image. Remember, it appears, well, that's the image, okay? This is the actual distance. Okay? All right. All right. So according to equation 18.7, S prime is equal to N2, the index of refraction of 2 over the index of refraction of 1, times what? Times S, right? Okay. Times S, okay? Now, let's differentiate in what is what. So we've got the observer is N2, and the object, in other words, what's being observed, is N1, okay? So we've got the observer, which is in air. Here's the person up here looking at it with their eye, okay? Looking down at it with their eye, okay? Looking down. So let's solve for S now. So S is going to be what? S is going to be the N of the air over the end of the plastic, times S prime. Oop. Or, excuse me, whoop, sorry. There we go. So S, object distance, N of air, which is 1. The N of the plastic, I didn't write that up here. N of air is, you should know that by now, is 1. N of the plastic is, you have to look it up, 1.58. Okay, you have to look in your textbook to find that, okay? Or excuse me, 1.59, not 1.58. And yes, you need to put 1 point. Don't tell me I just erased it again. There we go. 1.59. Okay. So let's plug everything in. So we got 1 over 1.59 times 2 centimeters. And by the way, we can leave it in centimeters. We do not have to convert it to meters because the index for fraction is unitless, okay? So in other words, the ratio will be the same regardless of whether it's in meters, centimeters, inches, feet, whatever, okay? The ratio will be the same. So we got 1 divided by 1.59 times 2, and we get oh, you know what? I think I boo-booed. Oh, I've got to add it. I'm sorry. All right, so we get 2 centimeters is equal to, yeah, I'd see what I did. Yeah, I see what I did. I did this backwards. Woo, Lord help me. I'm not paying attention. It's been a long day. All right, so actually I should have done what? I should have come over here and we get what? Man, why is my stuff erasing, okay? N2 and N1. All right, okay. All right, so let's plug all this. Let's go back and plug all this in. So we got 2 centimeters is equal to S, and that's 1.0 over 1.59. And so we get a fraction of what? We get 1 divided by 1.59. I'm sorry, divided by 1.59. And we get 0.62, 0.63. We'll say 0.63. So that's 0.63 S, and then divide 2 by 0.63. And we get 3.17. So S is equal to 3.17 centimeters, and that works out really well. I apologize for that, okay? All right, let's move on. Let's do one more. Let's look at number 45. Okay. Number 45. And this is on page 654. Okay. Okay. All right, so we have a 1 centimeter tall object. Okay, so we got an object that has a height of 1 centimeter. Okay. And it is 10 centimeters in front of a converging lens. Okay. So you've got a converging lens. Let me do this. Let me move this around a little bit. So the height, man. Okay. So the height of the object is 1 centimeter. Remember, y'all, you don't have to put it in meters because remember, this is we're dealing with fractions here, and so the relationship is going to be the same regardless, okay? The ratio is the same. Doesn't matter if it's in meters or centimeters, all right? And it's 10 centimeters in front of a, did it say converging? Yeah, converging lens. What kind of lens is that? It's a lens that looks kind of like something like that right there, okay? So it is 10 centimeters. So this distance right here is 10 centimeters, okay? All right. So S is 10 centimeters. So S is 10 centimeters. That's the object distance. All right. And the converging lens has a focal length of 30 centimeters. Okay. Wow. So the focal length, and I didn't really draw this, let me do this right here. Let me move this around a little bit. That way I can squeeze it all in maybe. All right, so here it is, 1 centimeter. This is, let me make that smaller. You got to keep everything to scale. So that's 1 centimeter. This distance right here, and I know it's not to scale, it's 10 centimeters. The focal length is way back here, okay? And it's 30 centimeters, okay? All right, now it says, we got to find the image position. It says calculate the image position and image height, right? Image position and height. So we've got to calculate S prime and the height of prime. So this is what's in question, okay? So we got, and remember prime is image, so this is image position and image height, okay? All right, image position and image height. All right, well, how in the world do we do that? Okay, well, we can take our lens equation, and we can say 1 over S plus 1 over S prime is equal to 1 over the focal length. And so let's solve for S prime. So 1 over S prime is equal to what? 1 over the focal length minus 1 over S, right? So let's plug everything in. 1 over S prime is equal to 1 over 30 centimeters. Remember, we don't have to convert it to meters because the ratios are the same, okay? And 1 over S, and the S was 10, right? 10 centimeters, is that right? Yeah. Okay. Okay. So we get a common denominator here, and what do we get? When we do the fractions, we get 1 over 15, and by the way, that is what? Is that a negative 15? It should be, yeah. It's a negative, yeah, it's a negative 15, because if you do the fractions, so you do 1 over 30 minus 1 over 10, you get a negative 1/15. So you get a negative 1/15, and so therefore S prime is what? A negative 15, and it's a negative 15 centimeters. So that is the image height. Boy, notice how much larger it is. Wow, it's 15 times, no, yeah, it's 15 times larger. Okay, all right, it is 15 times larger. All right, now how do we get the image height? Okay, well, the image height is obtained from what? Now that's the image distance, excuse me, not image height. That is the image distance. Okay, image position or image distance. Now how do we get image height? Okay, well, we know from our magnification equation, M is equal to what? It is equal to a negative H prime over H, or we can say it this way, a negative S prime over S. Okay? So let's plug that in, and we get what? Well, we get a negative S prime was what? S prime was a negative 15 centimeters. The units are going to cancel out, by the way, over what? 10 centimeters. And so we get a positive 1.5 magnification. So the image is 1.5 times the height of the actual object. Okay? Okay. I hope that helps.